Welcome back to the last module 4.2. As I told you, separation processes 2. I'm still Professor Engineer JC Igwe. We're going to look at separation equipment, sequencing of columns, selection of separation processes, and then we conclude. Separation equipment. Now, selection of this separation to solve these problems, usually the concept of equilibrium stage or based on diffusion rate processes. So you see, we're talking about two streams. That means there must be movement from one phase to the other. Mass transfer, heat transfer. So it's on diffusion processes, what we call transport phenomena. So here, the phases are brought into contact in stages. If sufficient contact time is allowed, the components become distributed in accordance with thermodynamic equilibrium conditions or considerations. So we're saying that this separation process takes place under heat transfer, mass transfer, momentum transfer, and so on. And based on that, once you have enough contact time, the species will migrate or be transferred from one phase to another, depending on the thermodynamics. Thermodynamics here now, we're talking about whether it is concentration gradient difference, whether we're talking about temperature gradients, we're talking about any condition like we said in the first module in terms of volatilities, difference in boiling point, difference in solubilities, and so on, which will determine the type of separation process to be used. We can also have multi-stage arrangements that can be used, and of course the number of equilibrium stages required for a desired separation is also calculated. Another type of device used in separation process is based on continuous contact of the phases, as in a packed column. So if you've seen a packed column before, for instance, if you get something like a measuring cylinder, usually we use that to construct a column. Once you have an opening down where you can control the nozzle, the valve, if something like a liquid is poured from top, just a simple gravity method from top going down, you see that the column, if it is packed with something like an absorbent, the absorbent will absorb certain contaminants in that column. For instance, if you want to clean up water, our activated carbon column, once the water passes through, there will be a kind of filtration by absorption, removing some contaminants in the water. So when the water, comes out, the composition will no longer be the same as initial contaminated water will have. So here, the compositional changes are continuous throughout the packing. Design procedures are generally based on mass transfer rates for rates that are integrated over the height of the region of phase contacting. Now, for both design methods, knowledge of the equilibrium relationship between phases is very important. Now, columns, we want to look at the type of ways that columns can be put together. I will say that is sequencing of columns. Now look at the columns. We have A, B, and C. One is counter current, one is co-current, and the other one is cross current. Counter current, stream 1 is going in opposite direction as stream 2. Now co-current, both stream 1 and stream 2, that is B, are going in the same direction. And then cross current, we can see why the stream 1 is crossing from up, the stream 2 is crossing from horizontal direction, going in opposite counter or cross direction. That's why we call it cross current. The counter-current flow arrangement, which is A, is generally preferred over co-current, that is B, or cross-current flow. An n-component mixture, remember we said that we can calculate, the number of equilibrium stages. So an n-component mixture would therefore require n-1 columns to separate the n-component mixture. So if you have 5 component mixtures, it means we are going to require 5 minus 1, that is 4 columns to separate that 5 component mixtures. Now consider a 3-component mixture comprising A, B, C, where the volatilities are such that A is greater than B, B is greater than C. Now remember that n-1, you can see the diagram. If it is a 3-component mixture, then we have 2 columns because n-1 will be 3 minus 1, which is 2. So if we are now required to separate this component, look at the possibilities A and B. Now, although one complex column can be designed to produce the desired product, a sequence of simple separators is commonly used. You can do that with one column, but it's not going to give you a very good result more than using, like in this case, 3-component mixture, we're using 2 columns. This is because it is frequently more economical than one complex separator. And if a simple separator does not perform relatively sharp split between the 2 component products. Now look at A and B. The first thing that happens is A, B, C comes in. Remember, volatilities, A is greater than B, greater than C. When it comes into the first column, A is separated, then B and C is remaining. A is more volatile, so A goes up first. B and C comes out from the first column, goes into the second column, and B is now removed and C remains as what we can call the residue, kind of. So you see A goes up first, then B follows, and then C, because of volatility differences. Now if you look at B, following the volatility again, ABC goes into the first column. The one that is less volatile, stays back as a kind of residue. Then AB is given off, which goes into the second column. Then A is given off, and B is also separated. So using both A and B patterns, which are 2 columns, we can separate 3-component mixtures. Now, some heuristic exists which allows choosing an optimal sequence of large number that exists for given separation. Among them are separations where the relative volatility of the key component is close to unity should be performed in the absence of non-key component. Sequence in which removes the components one by one in column overhead should be favored, which is what we have just shown. A product that constitutes a large fraction of the feed should be removed first. Separations involving very high recoveries of the key components should be reserved until late in the sequence. Now, we say in some instances, these heuristics may conflict with one another. So that is what tells us what and what to do. We'll try to consider, in trying to do the separation process, what and what to consider. Selection of separation processes. Now the question is, which process will you select for any particular problem? The underlying physical or chemical principles and phenomena must be clearly understood, like we mentioned in terms of volatilities. Do they have different boiling points? Okay, of course, that's the next thing there. The physical properties, molecular weight, normal boiling point, vapor pressure, solubility, melting point, density, and so on must be known. So for all the components, if you know all this, that is where you can now choose which particular separation process to use. Another thing, the economic value of the product being isolated can influence the choice of a separation process. For instance, if the economic value is not very important, and you go and use a separation process that is very expensive, then it means after separating that product, you will be at a loss instead of using a very simple method. When availability, you have a lot of options. Which one do you choose? Again, process feasibility may border on the need for extreme processing conditions. When you look at it, where you have extreme processing conditions, it's going to be very expensive. So you look at those processing conditions that do not require extreme conditions. Along the line of process feasibility, if there exists more than one physical process, the choice is based in favor of those processes whose design procedures are fairly well standardized. So we're saying that, for example, again, probably if the product is required in a very high pure form, that will also determine the type of separation process or separation device that can be used. Now, most times we have said that most of the industries what we use is distillation. So in any way the ordinary distillation is difficult, then we can follow the following factors to decide on which other separation process to use. One is simplicity. Where there is a choice, one should choose the process that is simple, that involves standard and well-known unit operations and processes. Investment costs, like I said, extreme operating conditions like high temperature and pressure, or the opposite, very low temperatures and pressure, and geometric complexity equipment inflate investment costs. Maintainability and easy operation. Avoid equipment that has unusual mechanical design, fragile construction, or difficult to maintain. In addition, handling of gaseous and liquid streams is generally favored over solid and slurries. Safety is another one. Adequate consideration should be given to safety of personnel and the environment. If you are going to use a separation process that is not safe, even for the people working there, then it doesn't make any sense that after carrying out the separation process, you're going to kill your staff or even your customers or even damage the environment. No, that is not advised. Thank you very much. We've come to the end of Module 4.2, and that's the end of the lectures on 351. In this module, we have looked at separation equipment, sequencing of columns, and selection of separation processes. Now, the next thing that will follow will be the assignments, the tests, quizzes, and of course, you're free, like I've always said, to ask your questions, and we'll deal with the questions as the questions arrive. Thank you so very much for staying all through the lectures, and I hope you enjoy the class and the aim of this online is achieved. Like I said from the beginning of the class, that we want a situation where, because of time, environmental influence, insecurities, and the rest of the stuff, and even cost of transportation running up and down, we decided that at least, and majorly again, for students to be able to listen to the class, a second time, a third time, as many times as they want, since you can download and, watch and listen and make your notes. We decided to blend the on-site lectures with the online lectures. So I hope to see you in the physical class, and then we'll discuss and continue with our assignments and other things before the examination. Thank you very much, and God bless you all.